Thank you, Kostas. And yeah, I'd like to start by thanking the organizers for the invitation to speak here. It's my first time in Athens outside the airport. It's a great pleasure. So today what I want to talk about is some ongoing, some work with three excellent students who are either just finishing or have just finished, and a collaborator of mine, Dan Thompson at Swansea, and also some ongoing work with Lewis Cole. And the goal of this work is really to understand the integral models that we get from holomorphic theories, as opposed to sort of the more traditional integrable models that we may be familiar with. And I'll introduce all these terms. So I'm just going to flash this. There are many reasons why integral systems are interesting in mathematical physics. I've listed some here. There are more. What's been quite exciting over the last couple of decades is that, last couple of decades, is that the landscape of 2D integral models has continued to grow. So typically this used to be done following an approach of direct construction. This can be very challenging, trying to find a lax connection for a given model. But more recently there have been sort of more systematic approaches, for example affine-Godin models or higher dimensional gauge theories. And also people have been using more general guiding principles such as dualities and deformations. And I should say that all these frameworks are closely connected. So today what I want to focus on is this third one in the list, this higher dimensional gauge theory story. So two approaches that, have been around various lengths of time are 4D Chern-Simons and 4D anti-self-dual Yang-Mills. So the idea of 4D Chern-Simons is to consider a gauge theory which has a Chern-Simons 3 form and an omega, which I'll introduce properly later. And you consider this theory on CP1 times R2, and you introduce some defects on CP1, and it localizes on these defects, this theory, to give 2D integrable models. The other approach is 4D anti-self-dual Yang-Mills, and this has actually been around a lot longer. And the idea is to consider solutions of anti-self-dual solutions of the Yang-Mills equations, which can be characterized in this way. There are different ways of characterizing it. And what you find is if you reduce this in a sense of symmetry reduction or dimensional reduction along 2 dimensions, you end up finding 2D IFTs. So Costello proposed and Bittleson and Skinner kind of formalized that you can sort of combine these two approaches into a sort of into a shape which, if you squint, is a bit like a diamond, in the following way. So you have here 4D Chern-Simons. If you localize this, you get some 2D IFT. If you consider this 4D IFT is meant to be anti-self-dual Yang-Mills. If you reduce that, you get to a 2D IFT, and you can sort of embed both of these inside 6D holomorphic Chern-Simons, which I'll introduce in a second. And if you reduce 6D holomorphic Chern-Simons, you land on 4D Chern-Simons, and if you localize, you directly get to your 4D IFT. So this was proposed by Costello, and a few years back, Bittleson and Skinner worked this sort of diamond out for one particular example, or a few examples, and showed that indeed such a structure can work. So this is the action of 6D holomorphic Chern-Simons. It's not super important, the detail. Again, we have a Chern-Simons 3 form, but now it just depends on the 0-1 component of a 6D gauge field. Omega is a 3 form. Again, I'll introduce that properly later. The action is now on twistor space, which in some sense you can just think of as CP1 times R4, but there are important features of twistor space which I'll come back to later, but for now we can just think of it as CP1 times R4. And if you localize on CP1, you get the 4D IFTs living on R4, and if you reduce along 2 dimensions in the R4, you get the 4D Chern-Simons on CP1 times R2. And actually you can also reduce along 1 dimension to a 5D Chern-Simons theory. So that sort of motivates a slight refinement to the diagram where you also get a sort of 5D Chern-Simons sitting in the middle here. Good. So I just want to make a few comments on this construction. So the 4D Chern-Simons and 5D Chern-Simons are mixed. And what I mean by that is that they're holomorphic topological. So for example, the 4D Chern-Simons is holomorphic in the CP1, but it's topological on the R2. Similarly for 5D Chern-Simons. The 6D Chern-Simons is a sort of fully holomorphic theory. So you can imagine that you're starting from 4D Chern-Simons and you're sort of complexifying dimensions and turning topological dimensions into holomorphic directions one by one until you reach 6D holomorphic Chern-Simons. To find non-trivial 4D IFTs from 6D holomorphic Chern-Simons, it's important that we're on twistor space, and in particular, this is what gives us the complex structure. So the complex structure on R4 depends on where we sit on CP1. So as we move around R4, the complex structure, as we move around CP1, the complex structure on R4 is changing. If you just use the details of that are not too important, but if you just use the trivial complex structure, then you would basically just end up with complexified 2D IFTs, which we don't want. So we want something a bit more complicated than that, something where, so these complexified 2D IFTs would only have derivatives in two directions. We want to have derivatives in all four directions of our R4, and for that we need this more complicated complex structure. And similar statements also hold for the 5D Chern-Simons and 3D IFTs. So this dimensional reduction story, it sort of goes right through the integrability, classical integrability structure. So the equations of motion of the 2D IFTs are governed by a Lax connection, 3D IFTs by the Bogomolny equation, and 4D IFTs by anti-Self-Julian-Mills. And these are all defined in terms of some spectral parameter defendant 1 form. These are just the notation I'm going to use throughout the talk for various things. And these are reductions of each other. So you can go from the anti-Self-Julian-Mills connection to connection satisfying the Bogomolny equation to a Lax connection. So, good. So that's one approach, in some sense, to going up in dimensions. So starting from 4D Chern-Simons, complexifying in inverted commas two of the dimensions, and considering 6D holomorphic Chern-Simons. There is actually an alternative proposal for constructing 3D IFTs. And in principle, this can be generalized to higher dimensional integrable field theories. And I'm not going to go into details of this model, but for the purpose of this talk, I'm just going to say it's a mixed 5D 2 Chern-Simons theory. So it's based on a Lie 2 algebra, and it has both a 1-form and a 2-form gauge field as its field content. So, as I say, the details are not super important, but the presence of the 2-form gauge field is interesting. In particular, if we think about conserved charges in higher dimensions and generalized symmetries, it's natural to expect that integrability in higher dimensions would require higher form symmetries or generalized symmetries, and the extended objects which would couple to higher form gauge fields would be important for this. This is sort of schematic, very schematic, and you can think about the sort of tetrahedron equation in quantum 3D integrable field theories and also membranes as kind of examples of this. So the goal of this talk is really to understand what the relationship is between these two different proposals. So one proposal for going in higher dimensions is to consider this sort of complexification, and one is this categorification. And the motivation for this comes from, in particular, this 5D Chern-Simons and 5D 2 Chern-Simons, and both Bittleson and Skinner, and then Schenkel and Vicedo considered these respectively, and both of them seem to get what's called the Ward model. So the Ward model, again, details are not important, but it's a 3D generalization of the principal chiral model. It's meant to be integrable, There are nice scattering properties and has kind of many of the usual features of integrability. So both seem to give the Ward model in a sense, and our question, what we want to understand is how is this related? How are they related? Another way of thinking about this is, so I was arguing up here that the two-form gauge field is important for symmetries, and in principle for integrability. But the 5D Chern-Simons and 6D holomorphic Chern-Simons, they still only have a one-form gauge field. So the question you might ask is, do the 3D and 4D IFTs constructed from these have the conserved charges that you would expect to be the hallmark of integrability? So I'm not going to work with 5D Chern-Simons. They are, well, 5D Chern-Simons in its higher categorical generalizations are tractable. You can work with them, but they are significantly more complicated than 4D Chern-Simons. So actually what we're going to do is we're going to simplify the story. We're going to go in the other direction. So it turns out that you can also construct 1D integrable field theories from a 3D mixed BF theory. So this is something that Vicedo and Winston were working out. And this 3D BF theory also has a holomorphic counterpart, which is known as 4D holomorphic BF. So our approach is going to be to look in more detail, take this 4D holomorphic BF theory more seriously, and look at the 2D IFTs that we get from it, and try to compare these to the 2D IFTs we get from 4D Chern-Simons. So I should say that this idea that this diamond might exist and that you can get 2D IFTs from 4D holomorphic BF is not new. There are examples in the literature, but they're kind of sporadic. So I have a diagram. So hopefully, I appreciate I've introduced many concepts very, very fast. Hopefully this gives a sort of sketch of what we're trying to do. So for those who are used to familiar 2D IFTs with a lax connection, that's basically sitting here. That's this 2D IFT. They come from 4D Chern-Simons. This diamond here, this pair of diamonds here, is the one I introduced first, where we complexify, and we go up to 6D holomorphic Chern-Simons, giving 4D integrable field theories. And these are the ones that are characterized by anti-self-Julian-Mills. In principle, we can jump up here to 5D 2 Chern-Simons and 3D IFTs. And we might ask how this pair of theories is related to this pair of theories here. But instead, what we're going to do is we're going to jump down here to 3D BF and 4D holomorphic BF and ask how this pair of theories, so 4D holomorphic BF and the 2D IFTs that you find from it, are related to 4D Chern-Simons and the 2D IFTs that come from that. Good. Before I continue, are there any questions about the goal of the talk, or everyone happy? So this is going to be the plan of the talk. I'm going to spend a little bit of time discussing integrable field theories from 6D holomorphic Chern-Simons. That's this diamond up here. I'm not going to mention 5D again. I'm then going to move on to this diamond down here, so the 4D holomorphic BF and the 2D IFTs you get from that. And then I'll try and sketch the relation between these two constructions. And then I'll list a bunch of open questions. Okay, good. So let me just start with what was known before we started to look at this. So Bittleton and Skinner, they constructed this diamond that I'm going to sort of keep track of down in this bottom right-hand corner, essentially for the 2D IFT being the principal Caro model plus the Western term. And what I'm going to mainly do is go through their construction in a little bit more detail to sort of give everyone a flavor of what's going on. early attempts to generalize this were complicated by the fact that it was unclear how to lift the boundary conditions from 4D Chern-Simons up to 6D holomorphic Chern-Simons, and it was also unclear what gauge symmetries to expect in the 2D and 4D IFTs. So we started to look at this question, and we managed to construct a diagram for a particular current-current deformation of the Westerminer-Witten CFT, which is also known as the lambda deformation of Svetsos. And we also looked at certain gaugings of the principal Carr model plus Westerminer term. So, okay, it's still two more examples, but I think by now we kind of have a pretty systematic understanding of how you would go about doing this in general. Good, so seeing as this is a low dimensional conference, I'm going to start at the bottom of this diagram. So what I've written here is the action of the principal Carr model plus Westerminer term. Hopefully it's relatively familiar to people. G here is a group valued field. We're in 2 dimensions on R2. J is the Mara-Cartan 1 form. This is the usual kinetic term, which if this second term wasn't here, would just define the principal Carr model. And then we also have the usual 3 form, the Westerminer term. K is quantized, it's the level, and H is the sigma model coupling. So when H is equal to 1, this is just Westerminer-Witten. And if you take H equals 0 in a careful way, you can recover the PCM. So we can compute the equations of motion of this model varying G, and what you find is the following equation. In particular, this is just the conservation equation for this particular current here, K. So D star K is just tells you that this is equal to 0. And actually, this, if you compute the curvature of K, you also find that on the equations of motion, it vanishes, and it's a sort of standard procedure in 2D integral field theories that if you have a flat conserved current, then you can construct a lax connection. So this is what I've written here. So L is defined in terms of this flat conserved current K, and zeta, so zeta is a spectral parameter, it's complex valued, and the flatness of L for all zeta is equivalent to the equations of motion. And this is a sort of slightly more technical detail, but the Poisson bracket of L, the spatial component of L with itself, takes a particular form known as Maillet form, and what this implies, what's important, is that this implies that we have conserved charges in an involution, and we have the usual tower of integrable conserved charges that we would like. So, yeah, this is the theory that we're going to be looking at that sits down in the bottom left, and we're going to look at, first we're going to look at this left-hand leg, how this kind of originates from 4D Chern-Simons. So I already briefly introduced the 4D Chern-Simons action. Let me introduce it in a bit more detail. So A here is a G-valued 1 form on CP1 times R2. So we extend our space-time R2 by the complex projective space. And we build the Chern-Simons 1 form for that space. And then we wedge that, because that's a 3 form, we have a 4-dimensional space, we wedge that against omega, which is some specified meromorphic 1 form on CP1. So it's meromorphic, so it's allowed to have poles, and they will be important. To define the theory, there's by now a very systematic procedure that you can follow. You first need to specify omega, so your distribution of poles and zeros. You can also change CP1, but for now to some other Riemann surface. You also then need to specify some data. In particular, we think of the poles of omega as boundaries. So we need to specify boundary conditions at these boundaries such that the boundary variation vanishes. And omega can also have zeros. And at those zeros, we can still have finiteness of the action if A has poles at those zeros. So, but those need to be finely tuned so as the poles in A don't overwhelm the zeros in omega. So, and we do this by imposing certain regularity conditions. The details are not particularly important, but this is the data that we need to define a theory. So omega, a particular one form, some boundary conditions at the poles, and regularity conditions for the connection A. The boundary conditions break the gauge symmetry, and what we then find is that there's a effective 2D IFT that lives on the boundary as a result of this gauge symmetry breaking, and this is just the edge mode theory. So these are, you introduce some bulk fields, and the edge modes that live on the boundary give this 2D IFT. And I should say that depending on how mathematical you are, you have a range of approaches available to you. So for the principal Chiral model plus Wess-Zumino term, this is the particular one form that we use. So it has two zeros at plus or minus 1, so zeta equals plus or minus 1. And we also have a double pole at zeta equals h, which I just represent by this random point here. And finally, we have a double pole at infinity, which you need to go to 1 over zeta to send zeta to 1 over zeta to c. So I'm not using zeta accidentally. Zeta is here the complex coordinate on CP1, but it will also become our spectral parameter. So I should note that here I've done a little bit of fixing. So using the SL2C on CP1, so I've just chosen to put my zeros at plus minus 1 and 1 double pole at infinity as a matter of convenience. But you can always fix 3 of your points as usual. And then the remaining degree of freedom, or the remaining degree of freedom, is the position of the double pole on the finite plane. So in this talk, pretty much everything we will consider are Dirichlet boundary conditions. So we can just basically say that the R2 part of the gauge field A vanishes at both double poles. We then define, or we redefine A in terms of G hat and L in this way. So basically the zeta bar component of L is chosen to vanish and is completely absorbed into this G hat field. So here G hat is a group valued field evaluated on the whole R2 times CP1. I'm not going to crank the handle today, but you can then partially solve the bulk equations of motion subject to the boundary and regularity conditions, and you find that G hat contains a bunch of edge modes that become the fields of your 2D IFT, and L is then the lax connection of your 2D IFT that depends on L. So there are a number of very clear papers where this procedure is described. And then you basically substitute this back into the 4D Chern-Simons action, and you find the 2D action of the PCM plus Wess-Zumino term. And as you want, the equations of motion of the 2D IFT are equivalent to the flatness of the lax connection. Okay. So let me jump over that. So we can now jump up in dimension to 6D holomorphic Chern-Simons. Not here, I'm just considering on R2, yeah. That's an interesting question. There has been some work on that. I think maybe even Bittelson and Skinner had a paper on looking boundaries in 4D. I'm not an expert exactly how that works, but it's an interesting question. yeah, I think they looked at like K matrices instead of R matrices appearing, but yeah, I don't remember the details. Okay, great. So this is 60 holomorphic Chern-Simons. It's defined over twistor space. Here, omega is some specified. Now it's a 3 form. In particular, it's a meromorphic 3-0 form. And a bar is a 0-1 form on PT. So details are not super important, but this has a complex structure, and this splitting is with respect to this complex structure on twistor space. So so many of this is basically a copy of what has already come. We define the theory by specifying omega. This should be capital Omega here, boundary conditions at the poles, and regularity conditions for the gauge field. The boundary conditions break the gauge symmetry, and the 4D IFT is the edge mode that lives on this boundary. So the mechanics is very, very similar. This is the particular meromorphic 3-0 form that we consider. Pi, I'm now using homogeneous coordinates on CP1. So pi is identified with itself up to a scaling. XAA dot are my coordinates on 4D space-time. So we can introduce a particular basis of coordinates on the 4D spacetime, ZW, Z bar, and W bar. And if we then reduce along Z and Z bar, we find that we go from 60 holomorphic Chern-Simons to 4D Chern-Simons. So this is just a sketch of how this works. If we basically take omega and we contract with the direction, the vector fields dz and dz bar, and rewrite homogeneous coordinates in terms of inhomogeneous coordinates in this way, it's a familiar way, what you find is that a one form omega that is exactly the one form that we had that we used for 4D Chern-Simons. So that corresponds to going this way around the diamond. It's also possible to go the other way around the diamond, and in this case we find a 4D IFT in the middle. So again, we take Dirichlet boundary conditions, we introduce a bulk G-valued field such that this A bar of zeta bar, this curly A bar of zeta bar is equal to 0. We substitute this back into 60 holomorphic Chern-Simons and we find the action of a 4D IFT. There is an analog of the Lax equation, which is basically this equation here, which is equivalent to 4D anti-self Joule-Yang-Mills. So this is the particular 4D IFT that we find. It's a theory over R4. It looks very similar to Westermino-Witten. J is again a Morikawa-Tan form for a G-valued field. Omega alpha beta here is a specific 2 form that depends on these on spinors alpha and beta, which parameterize the positions of the poles. And this is explicit formula here. The main point I want to make here is this model does not have SO4 Euclidean symmetry, or in Lorentzian signature SO13. That's broken by the presence of this omega alpha beta. So yeah, this is just a caveat to say that when I'm talking about these higher dimensional integral field theories, I'm not necessarily talking about Lorentz invariant field theories or Euclidean invariant theories. We're in a sort of slightly more general setting. I don't know. It may be related, but I don't know. So yeah, just to finish off this example, you can compute the equations of motion, and what you find is that they're equivalent to the anti-self Joule-Yang-Mills equations for this particular connection here defined in terms of G. And just as for 4D Chern-Simons, you can find this directly from 60 holomorphic Chern-Simons. So my final comment before I move on to 4D holomorphic BF is is just a general. This is more sort of a general comment about how to generalize this whole construction. So, in particular, we can think of dualities. We can understand dualities and deformations in terms of these one form and this one form omega, or the 3-0 form capital omega. So, for example, dualities can be understood as choosing different boundary conditions at different for the same configuration of poles, whereas deformations could be understood, for example, as splitting a double pole into two simple poles. And this is where a lot of the subtlety lies when you try to generalize this 4D Chern-Simons to 2D IFT into this full diamond. In particular, many of the boundary conditions that you want to consider for 4D Chern-Simons don't easily lift up to 6D holomorphic Chern-Simons, and you need to consider wider classes of boundary conditions. Okay, good. So that's my summary of this diamond here, starting from 6D holomorphic Chern-Simons. Are there any questions at this point before I move on to holomorphic BF? So the idea is very similar here, and here I'm not actually going to describe the full diamond. I'm just going to focus on this particular right-hand side. So 4D holomorphic BF to 2D IFTs. So this is the action of holomorphic BF. So it's defined on now CP1 times R2. This looks like the same thing that 4D Chern-Simons is defined on, but now we want to consider this as a holomorphic theory. So omega is now a meromorphic 2-0 form with respect to some non-trivial complex structure on this CP1 times R2. A bar is a G-valued 0-1 form, and B is a G-valued scalar that just imposes that A bar is flat. And again, the story goes the same way. To define the theory, we specify omega. The boundary conditions are the poles of, again, capital omega, and we that ensure the boundary variation vanishes, and we impose regularity conditions for A bar and B, actually, and B. The boundary conditions break the gauge symmetry, and the 2D IFT is the edge mode theory that lives on the boundary. So the mechanics is, again, the same. The example I'm going to discuss is this particular 2-0 form. So I'm using, again, the same notation in terms of the homogeneous coordinates on CP1. The important thing to notice is that omega has three simple poles. So there's a pole at pi equals alpha, a pole at pi equals alpha tilde, and a pole at pi equals beta. And we're, again, just going to take Dirichlet boundary conditions at each of those poles. And then following a similar procedure to 4D Chern-Simons and 6D holomorphic Chern-Simons, I'm glossing over some additional subtleties which are interesting, but they are subtleties. We find a 2D IFT. And this is the 2D IFT that we find. So this, if you are familiar with 2D IFTs, well, if this is familiar to you, I'd be very interested in talking to you. But for us, this was quite a strange theory. So d alpha, partial alpha and partial alpha tilde doesn't really matter what they are, but they are just two directions in R2. So they are derivatives along two different directions in R2. This theory depends on two group-valued fields, G and G tilde. And actually, this action has a number of features that are very similar to the 4D IFTs that you get from 6D holomorphic Chern-Simons. So, in particular, d alpha derivatives only appear acting on the field G. D alpha tilde derivatives only appear acting on the field G tilde. This theory is not invariant under Euclidean or Lorentzian space-time symmetries if you consider it on R2 or R11. So, for example, in R11, you could try to say alpha is the plus-like cone or alpha tilde is the minus-like cone, but you cannot make this Lorentz invariant. You can also, there is another way of thinking about it which also lifts to this 4D IFT story, which you can think of as sort of coupling coupling two 1D IFTs. So you can think of, if I expand out this square, I get a theory which is just d alpha g, g inverse squared. So that's one 1D IFT sitting along the alpha direction, and I have another one for G tilde sitting along the alpha tilde direction, and I'm sort of building a 2D IFT by sort of coupling these two 1D theories. It's, again, very schematic, but that kind of structure also appears in the 4D Chern-Simons. And I should say that it's that thing it's that property which comes from the fact that you've considered a non-trivial complex structure. So because these fields come from different points on CP1, the complex structure picks out different directions. And that's what allows you to have something that's not just a complexified 1D IFT. So you can compute the equations of motion. You don't get something which is like a normal lax connection. You get something that's more similar to a 1D IFT. In particular, the equations of motion are equivalent to the covariant derivative of B vanishing for all values of the spectral parameter. Nevertheless, you can still use this to construct conserved charges. You can consider the monodromy of B. You can also compute the Poisson bracket of B, and it satisfies Poisson bracket of Skleanin form, so it's ultra-local. So for those of you who are familiar with the space of 2D IFTs, this means that it's kind of on the kind of simpler side of 2D IFTs, which you may kind of expect, because it at the end of the day is a weird, but it's a very simple looking theory. So, okay, that's the example I want to use, but now I just want to sort of conclude by sort of sketching this relationship between 4D Chern-Simons and 2D IFT, and 4D holomorphic BF, and the 2D IFT that comes from that. So this is an idea that's been around a long time, but it's known, well, at least certainly for 3D Chern-Simons, and you can generalize it to 4D Chern-Simons, but it's known that starting from the action of 4D Chern-Simons, which I've written again here, you can basically pick out a direction. You have freedom in how you pick out this direction, but we're going to pick it out in this particular way. And you let the coefficient of that field scale with 1 over k. So notice I've introduced a level or a parameter k sitting outside this 4D Chern-Simons action. We're then going to take the k goes to 0 limit. So you can go through the algebra, and what you find is exactly 4D holomorphic BF plus some boundary term. This is the particular form of the boundary term here. And omega, well, I'm not going to expect you to remember the formulae I wrote down, but basically you find that the particular one forms from 4D, the one form in 4D Chern-Simons and the 2D, and the two form in 4D holomorphic BF are related in the following way, and that's exactly what we want to relate these theories. So the first comment is about this boundary term. You may worry about it. It's interesting. It has to be there. It has some nice properties, but actually it doesn't change the 2D IFT that you find. So at the end of the day, it doesn't do anything. So we're just going to ignore that. And what you can do, which is construct a particular 4D Chern-Simons setup and a 2D IFT, such that you can basically replicate this limit in all of these different things. So at the level of the boundary and regularity conditions, to the level of on-shell solutions, to the 4D Chern-Simons theory, at the level of the 2D effective 2D IFTs, at the level of the lax connection, and at the level of the Poisson bracket. So this is exactly what we wanted, right? This is a relation between integrable field theory that comes from IFT, an integrable field theory that comes from 4D Chern-Simons, and there's a particular limit which gives us an integrable field theory that comes from 4D holomorphic BF, and we can trace that limit through all these different things. So this is a substantial link between the integrability structures in the 2D IFTs. So just to sketch something, you can kind of see how this would come from a lax equation where basically the component anything that's linear in B dominates because it's been scaled by 1 over k, and you've taken k to 0. So the remaining part of the remaining term that you would get from a flatness equation is basically dropping out to scales like k. Yeah, exactly. So if you compute the Poisson bracket, you'll get. So yeah, I didn't say, but this 4D Chern-Simons setup here gives a non-ultralocal 2D IFT, and you can compute the Poisson bracket of that, and it's yeah, you'll see exactly that delta prime term will scale with k and go to 0. Good. Yeah. So I'm close to time. Yeah. Fine, yeah. So let me just quickly summarize. So I won't spend super long on the what we've done, but essentially for the 6D holomorphic Chern-Simons diamond, we've constructed this diamond now for various examples, and there are sort of various interesting things we've learned about 2D IFTs. For 4D holomorphic BF diamond, we've now constructed this diamond for a couple of examples, and for both of these examples, we've managed to construct a 4D Chern-Simons 2D IFT setup that has, as a limit of that, the 4D holomorphic BF 2D IFT, and again, it runs through all of these different properties. There are various there are many kind of interesting future directions that one could try to explore. So I didn't mention disorder order defects at all, but the poles that we had in the omega are known as, or the zeros and the poles are known as disorder defects. There are also another class of defects which are known as order defects, where you just couple the 4D Chern-Simons to additional fields, and it would be interesting to see if you can generalize these constructions to the presence of order defects. Something I mentioned at the beginning, can we replace CP1 by some more general Riemann surface? There's been some works in this direction, but it's certainly an interesting question. Can we construct elliptic models, and et cetera, et cetera? So I mentioned that the Poisson structures, I sort of mentioned a bit about the Poisson structures. So in particular, this Poisson structure I mentioned for the 4D holomorphic BF looks very much like a Poisson structure of the 1D IFT. And similarly, one might imagine that the Hamiltonian analysis of the 6D holomorphic BF and 4D IFTs looks very much like the Hamiltonian analysis of 4D Chern-Simons and 2D IFTs, and it'd be interesting to study that in a bit more detail, how they are related. Finally, the bigger sort of questions, can we generalize the limit from 4D Chern-Simons to 4D holomorphic BF to higher dimensions? And can we understand this limit at a quantum level? Is that possible? It's not something we've looked at all. So I'm just going to finish with a sort of speculative diagram, which I am aware I'm being recorded, but everything up here is very, 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 very speculative. And so these bits in bold, I guess, are the bits that we claim to have some understanding of, and I guess you could imagine going off up into this world. So for 4D IFTs, you may imagine you have a 6D 3 Chern-Simons with a 3-form field as well, and who knows, maybe all this is kind of forbidden for another reason, but it would be certainly interesting to explore. Thank you very much.